Hi everyone, I'm Alain Demortier. I'm currently working in Météo France in France, and I'm working with Olivier Caumont, Vivien Pourret, and Marc Mandement. So my work is on sourcing new type of observation that we can assimilate in our AROME-France system. So actually we have here we only speak about surface observations. Actually, we have we called surface standard weather stations, which are our current network that we assimilate in AROME-France. Here you have an example of a station close to Toulouse. And currently, we have a lot of new stations which which are available, you can use. So they are called here personal weather station because they are different from the standard weather station. Here, they are owned by people. So we take stations from the Netatmo company, which has 55,000 stations only in France. It has an heterogeneous quality, but it has a lot of stations. I don't mention here, but there is a lot of different other networks called semi-professional networks coming from associations or public organizations. So here we are speaking about those stations, Netatmo stations. So where are they? So the standard weather station, SWS, the current network that we are assimilate, we assimilate in AROME, is homogeneous. So you can see that there is a station quite everywhere in France. There is more station of temperature than in relative humidity. And we have now some stations which are available called personal weather station. And you can see that those stations are owned by people. So they are more dense in cities like in Paris here. And there is thus much more observations to assimilate. 25 more. So we have done past studies assimilating pressure observation from those personal weather stations. I have shown a presentation in ISDA last year, and we have published an article to present the results. So positive impact in average in the surface and a better location and intensity of MCS case. And now I will present the work on the assimilation of temperature and relative humidity observations. So in the literature, you can see that there is much more article using those observations, but those observations needs a pre-processing, needs to be pre-processed. And so we have to use bias correction and quality control to reject observations which are not usable. And then literature used a thinning to reduce the number of observations for in cities, for example, where there is a lot of observations. So there has been one article trying to assimilate those observations of temperature and relative humidity in ICON, showing a neutral to positive scores. So the idea is to do the same in AROME-France operational model. So what is the impact of this new network? So I will not show the pre-processing that we have done here, composed of a bias correction and a quality control. And the most important here, we have thinned the network at 8 kilometers horizontal resolution to reduce the correlated errors that can occur. So AROME-France is our Météo France limited area model. It has a 1.3 kilometers horizontal grid spacing. It has 5 control variables, which includes temperature and specific humidity. And actually, it used a 3D VAR detachment scheme. And we are testing a 3D and VAR detachment scheme, which use an ensemble of members, 50, and a localization at 25 kilometers at the surface. So here you can see the domain of AROME-France. And in the next slides, you will see experiments that we have done, assimilating temperature, 2 meters temperature observation from those personal weather stations in the operational 3D VAR system. And we have done exactly the same in 3D and VAR, and exactly the same with relative humidity observations. So those experiments have been done during 1 month. Just to see the impact of one single observation, the impact is really different when we are using a 3D VAR data scheme or a 3D and VAR. Here I put a single observation experiment. So when you assimilate in AROME-France the one observation of temperature, you know the result that we have isotropic propagation of the observations. So here it's temperature increments. And when you do it in 3D and VAR with the B matrix, you have really more localized increments. And you have really much, it's really impressive. You have different propagation at each time step, which are not isotropic. So it's the same with relative humidity. When you assimilate only one observation, the impact is really different. So we have done some experiments, some 1 month experiment assimilating those new observations. In 3D VAR, so when we assimilate, it's called 3D VAR T. When we compare to the 3D VAR reference experiment of control, you have a degradation when we compared to the 1 hour forecast when we compare the standard weather station to the 1 hour forecast. You have a small degradation. And when we assimilate them with the 3D and VAR, we have a small improvement. So that's nice to see that when we assimilate those new network in 3D and VAR, we have improvements in temperature. And we have exactly the same pattern with relative humidity observation. When we assimilate in 3D VAR, we have a degradation. And when we assimilate in 3D and VAR, we have an improvement. That's for the same variable, but you can see that you have some impact on other variables also. This improvement that you can see when we are looking at OMB, so observation managed background, so the 1 hour forecast, you can see also up to 3 hours of forecast. And after 3 hours of forecast, you cannot see the improvement. So in average, at least you have 3 hours of significant improvement with the 3D and VAR that you cannot find with 3D VAR. So just coming for the different data achievement scheme. So the data achievement scheme, and it is really important to take advantage of dense network of observations. And just to see one example, one case, I will present here a score line. So it's a case of a score line crosses Agen, which is a city in southwest of France, which has dropped 130 millimeters of rain in 3 hours. So that's huge, and which has led to floods in Agen. So when you look at the experiment of control, so that's the near surface temperature analysis with the experiment of control. And in black, you can see the observations, the radar reflectivities. So under the radar reflectivities, you have a cold pool, you have colder temperature, let's say. And so that's to see that the control experiment is able to represent the score line, but in front and behind the score line, you have bigger cold pool. So when we assimilate the temperature observation from this new network of observations, this new network of observation can be seen with cycle on this image. And you can see that you can constrain the analysis, the near surface analysis, in front here, you can see, or behind the scroll line. So with the assimilation of new temperature observation, you can constrain the analysis. So here it's cycled experiment in this case. And when we assimilate relative humidity observation, it has also an impact on temperature filed with the B matrix, with the covariances. And you can see that we also constrained the temperature analysis. Just to see what's happened with when we add this new network, we have done a cross section here of the scroll line, and we will show the increments when we assimilate this new network. So when we look at the cross section of the scroll line here in the center between 0.5 and let's say 0.8, you have the rainfall, and the cold area, and here we see the analysis increments of temperature in the whole troposphere, and we can see the synergy of observations. So if we decompose all the different observations, if we assimilate only ground-based GPS, you can see that we have a small we diminish the temperature in the center of the scroll line. When we add the satellites, in this case, we do not change anything. When we add conventional observation, mainly composed of standard weather stations, so you can see that we have added some increments near to the ground. So we have reinforced the cold pool, so a cold area here and a warmer front and behind. And the last difference between those two images is the assimilation of the radar, the reflectivities, which lead to a colder troposphere. And at the end, when we assimilate the new network of observation called the personal weather stations, we also increase the cold pool. So we add the cold temperature here, and we warm behind and in front. So that's to see the impact of this new network, limited to the surface, let's say the boundary layer, but in synergy of all the other observations. So at the end, when we launch forecast from the analysis that I have shown before, so we launch a 6-hour forecast of rainfall, and you can see that in the observation we have this scroll line with a maximum of 93 millimeters of rain, and in the experiment of control we have only 59 millimeters of rain. And when we assimilate temperature observation from this new network of relative humidity, we increase the the maximum rainfall area here. So we have an improvement of the forecast. So that's the case for the northern part of the scroll line, but you can also see that we have diminished the southern part of the scroll line compared to the observation. So that's not better every time, but for the maximum values, it's okay. So to summary and conclude, the idea here was to assimilate a new network of observation owned by people, which has led to an assimilation of 3 and 6 times more observations than the current standard weather station observations. It leads to a reduction of the root mean squares observation minus forecast of the standard weather station observation up to 3 hours range. So that's in average with the Vivien scheme. And we have shown in the study case here that it can allow us to constrain the near surface temperature analysis during the scroll line with the 3D ENVAR data assessment scheme. So I have not shown here, but one problem with our 3D ENVAR system is that it is underspread near to the surface. The ensemble used to produce the B matrix is underspread near to the surface. So we give a lot of weight to the background and not enough to the observation near to the surface. And when we assimilate more observation near to the surface, we can reduce this bad effect. So that's nice to assimilate more observation near to the surface. And we have shown that in 3D VAR data assessment scheme, with this current configuration, assimilating dense network of observation is not ideal when thin to at 8 kilometers. So the idea could have been to increase the scale of the thinning if we want to use the 3D VAR. So the outlook will be to assimilate personal weather station of temperature, relative humidity, and surface pressure concomitantly now that we have tried to assimilate them independently. What is really important for us is to improve the long-term forecast of mesoscale phenomena. So we have to try the other mesoscale phenomena if we want to to prove the significant improvement. And we have to test the assimilation of this new network of observation in future DIA schemes when they will be available. For example, the 2D NVAR, which is developed currently for the surface, or the 4D ENVAR for the atmospheric component. Thanks for your attention.
Thank you very much, Alan. We already have 2 questions. One is from Ashish, and he's asking, what is the length scale fixed for a single ops test? And did you carry any sensitivity experiments with them?
The length scale, maybe he was thinking about this single observation experiment.
Yeah. Yeah.
We do not in 3D VAR take any length scale. It's just so here what we can see is that when we assimilate one observation in 3D VAR, it goes up to 100 kilometers here. So that's the typical length scale in 3D VAR. And in 3D VAR, we have a localization at 25 kilometers for the lowest level in the atmosphere. So it's 25 kilometers.
Okay. And so you didn't test any different setups? For
Not yet. It's a really good question. Actually, we think that if we change the localization in 3D and VAR, it could change the results, but we will have to also maybe be careful about the B matrix that we use in 3D and VAR also for that. Okay,
thanks. And the other question is by Ricardo, and he's asking, why does 3D VAR perform worse than 3D ENVAR with the 2 meter temperature and relative humidity? This was, I think, also related to these single ops experiments.
It's not always degradation. For our case, is that we think that when we assimilate dense network of observations, it's not a good idea to have really big increments like that, because the observation is not localized, and when you assimilate a lot of observation, you just add increments. So it's not perfect. That's we are showing that adding a new network of observation is really linked to the detachment scheme that we are using. And for our case, the 3D and VAR is better when we want to assimilate dense network of observation.
Okay, then I think this table was just a bit confusing.
Okay.
So after all, the 3D and VAR, as you said, is better than 3D VAR.
Yeah.
Okay. Yeah. Thanks. I think that answers the question. So thank you very much.